Hello and welcome to the last lecture of the lecture series called Let's Game It. This being the last lecture, we are going to keep it as short as possible, and at the end of the lecture we are also going to give you some directions that you can follow to go forward, or you can make your own choices. So I'm just going to give you a few pathways that you can trade on. So with that very brief introduction, let us start. So let us game it. So what are the contents today? So today we are going to deal with an economic model per se, which is called Kuno's quantity competition, because so far we have dealt with many other real life situations, but hardly any model or any scenario which has close or uh, complete resemblance with what we get to study in economics. So we're going to deal with a model like that. It's called Kuno's quantity competition. Then we're going to talk about the topics that we could have or should have covered but we could not, and we would love you to cover in your own free time, or if you want to pursue this pursue this particular subject in the future as well. So we're going to talk about those topics under the heading more topics. Then we're going to tell you new paths that you can trade on, new emerging trends that have come up, and then last but not the least, miles to go, or the conclusion for the concluding lecture of this series. So with that, let us go to the Kuno quantity competition. Now many of you might have already heard about this, many of you might already know this, but those who are new to this, for them let me give a very brief introduction to what this quantity competition or this model is. Kuno competition is an economic model in which competing firms choose a quantity to produce independently and simultaneously. So what, based on the knowledge of ours that we have built so far, we can conclude from this is that it's a simultaneous move game. It's a duopoly, so there are two competing firms, and it's named after French mathematician Augustin Kuno, and that's why it's called Kuno's quantity competition. This model applies only when these two firms that we're talking about produce identical or standardized goods, and they cannot collude or form a cartel. That is prohibited. And last is, it's a perfectly competitive market. So we're directly jumping into the solution part. So what I mean by solution is, so there are two firms, each of them has an identical cost function. It's called the identical cost function, is given by this. Now why this y variable take y1 value when you're talking about firm 1 and y2 when you're talking about firm 2. Here there will be a minus sign. I'm sorry, I forgot to put this over there. This is the inverse demand function for the firm's output, and where q is the total output, so q in other words can be written as y1 plus y2, because y1 and y2 are the outputs of two competing firms in the market. So what is our job? Our job is to find out what is the output in the Nash equilibrium. Now you can very easily understand that why it's called a quantity competition, because the firms are competing on quantity. They're not going to touch the price. The price is given. So what are we going to do? First, we have to find the firm's best response function. So many of you must have already, those who have seen our previous lectures, they have already have had some idea about what best response is. So I'm not going to tell that again. So we have to find out the best response functions of the firms. So firm 1's profit is basically price into quantity minus cost. So quantity, as you must what this is the price. Price is given by 120 minus q. Q can be written as y1 plus y2. So 120 minus q means 120 minus y1 minus y2. This is the price, this is the quantity for the firm 1. So price into quantity, total expenditure, minus this is the cost, 30y1, because it's firm 1. So expenditure minus cost is your profit. Now this is your profit function. Now you have to, what they are dealing in quantity realm or quantity sphere. So their choice variable is quantity. So taking the derivative of this profit with respect to y1, that is a quantity that a firm 1 is producing, holding y2 constant, and then setting the derivative at equal to 0, this is the first order condition, we get something like this, or precisely this. Now this is the best response function for firm 1. Similarly, firm 2 also we can get, which I am not going to do, which I assume that you will do. So let us go to the graphical methods. So this is how, this is the firm 1's best response function that you can plot on the graph, okay, on a y1 and y2 sphere. That means this is the y1 and this is the y2. Now these are the firm 1's, so let's go to the firm 2. So once you, this is the firm 2's best response function. This is a linear function, and how you plot a straight line, it's very straightforward on a graph. So what is the best response? So this is the best response of firm 1, this is the best response of firm 2. So what is the Nash? Nash will be where the both these best responses intersect, which is this. So how do you find out this number? So it's basically solving two equations simultaneously. So what you have to do, you can use many methods. We'll use the method of substitution. So what are we going to do? We now find a pair y1 y2 of outputs with the property that that means the best response functions hold. Now these are the this is y1, this is y2. This you must have got, I hope you must have calculated this on your own. Now substituting one equation in the other and do the method of substitution or method of any other method of solving two simultaneous equations can be applied. Once you get that, you will see that you are getting y1 to be 30 and y2 to be 30. That means y1 comma y2, our Nash is basically 30 comma 30. So this is how we typically solve a problem or an economic problem by using the tools of simple optimization techniques, or I would say the simple method of substitution, simple maths. Okay, there is nothing hard in this. Now if you have already got y1 and y2, so you can very easily find out each firm's profit by just substituting those numbers in the equation. Okay, so you may find many other complicated models in the future when you deal with this kind of situations, but this is going to form the basis of that. So if you can understand these simple models, understanding those a bit more complicated models will not be a big deal. Now there are many topics in game theory, and day by day it will only grow, because research is not going to cease to exist, right? The topics that we thought that we would be able to cover, but we could not, and given this knowledge, the basic knowledge that we have grasped, that we have achieved, secured by going through these lectures, we believe can help you to trade on these unknown paths. But these paths will no longer remain unknown if you just start trading on them, and you will be able to grasp each and every topic, I assure you, if you have listened to the lectures that you have given so far. So this is the uncertainty in information. So far you have talked about perfectly situations where the information is perfect, but what about the information is imperfect? There is uncertainty, there is risk involved. You can use models of uncertainty information. Then there are repeated games, both finitely repeated games and infinitely repeated games. Then there are evolutionary games. This particular part is very interesting, where you talk about there are two different kinds of people who are there in the market or in the economy or in the country, and then there is there's one person or third species which is entering into this new world, and then what happens, which species survives, which one dies. That's what evolutionary games will talk about. This is also partly, I would say, based or motivated by evolutionary biology, because evolutionary biology talks about cell formations, how cells react, how cells grow, and evolutionary dynamics. That evolutionary games in social science take motivation from the principles of evolutionary biology. Then there is mechanism design, which is basically a principal agent kind of a model, where there will be a principal and there will be an agent. So the principal will try to devise mechanisms to influence or make agents do or follow certain things, and how agents react or do not react and what happens because of that is what forms the crux of mechanism design. And there are so many that we cannot just list them all. So these are few of the topics that we thought we'd cover, but for some reason we thought that we'll leave it up to you. Now, new paths. As I have said already, and I must have mentioned in bits and parts in the previous lectures, that the game theory has expanded, has been expanding, and will expand in the future as well. And it has a very unique feature in it, that you can use this in different fields, in psychology, in economics, in mathematics, in physics, in quantum mechanics, so on and so forth. And the interrelationships of these kind of two different fields are what producing the newer paths. Behavioral game theory is one such new path. So I thought that I will not give introduction to all these new paths which I want you guys to trade on. So I'll just pick up one quote from one such famous mathematician or philosopher or economist who has said something about that particular theory. So this one is from John Nash, who says that I feel personally that the study of experimental games, which is the behavioral game theory, is the proper route of travel for finding the ultimate truth in relation to games as played by human players. So John F. Nash, we consider him to be the the father of modern game theory, has also stressed the importance of behavioral game theory. So what it does is it actually deviates from the rational economics and assumes that humans do not behave like robots. They are humans, they have emotions, they sometimes commit mistakes, and they do not take the right decisions always. And based on that assumption, they have built something called behavioral game theory. It's very interesting. You can look at that. Then we go to something called epistemic game theory. Epistemic game theory is nothing but a broader generalization of the classical game theory. They bring in the concept of, I would say they have the concept of rationality, now they bring in the concept of uncertainty. And with both of these things, they develop something called an epistemic game theory. And you'll be surprised that the person who is giving this quote, Robert Stalnaker, if I have pronounced it properly, he is actually a philosopher in MIT. So you see, a philosopher is giving or talking about a field which is known as epistemic game theory, and he's one of the forerunners in that, one of the pioneers in that. And a philosopher is talking about a mathematical, the concept which might seem very mathematical to many. And that's where my point comes into the picture, that it's not like only mathematicians or economists will use, even philosophers, psychologists, anyone who is interested can use it. Then last but not the least comes the quantum game theory, and this I picked up from one of the papers written by these four people. So what quantum game theory does is, there is principle of uncertainty in economics, we all know that. That seems to be the fundamental concept in both physics and the theory of information. Hence, that serves as the natural link between the two disciplines, that is the quantum mechanics as well as the game theory, or so to say information science. And that's what forms the core of quantum game theory. So you see, even those who are interested in physics or quantum mechanics can also use game theory in their field. So now, miles to go. As Khalil Gibran has once truly said, that when you reach the end of what you should know, you will be at the beginning of what you should sense. So I believe, along with my colleague Unninar and Kuru, we both believe that this small endeavor from our side that we have taken have benefited all of you. or at least some of you, in some way or the other, even in the slightest possible way it has benefited you or any one of you, then we would consider this effort of ours to be completely fruitful. And I hope that you have got a hold of the basics of this uh, beautiful subject called game theory, and this will encourage you to go further, to go many more miles before we all sleep, and it must have given you the sense of what you should do next. So with that, with the information that we have provided, we believe that it's time to say goodbye. Thank you for tolerating us, putting up with all our small mistakes that we must have committed, uh, to the technical difficulties that we might have faced at times, or to the maybe poor presentation skills that we might have showcased. For all those things we apologize, and even if it helps any one person, even a one person gets or derives some utility by going through these lectures, we will be more than happy. With that, I, along with my partner, colleague Unni, sign off, and we thank you all for being with us till the last day. Thank you.